As we move forward with our coverage of enzymes, it's really important that we make sure that we remember why we're doing what we're doing. That is, we really want to be able to know the catalytic rate and efficiency of an enzyme. We've been speaking about alcohol dehydrogenase and just how quickly and how efficiently can it detoxify ethanol. So as we move forward with that, we want to be able to look at we want to be able to quantify. We want to be able to give a quantitative value to these things. And so we want to have an equation that allows us to express the velocity of an enzyme as a function of substrate concentration. So in order to move forward in the derivation of that equation, I'm actually going to begin by looking at the graph, the function that will result when we graph that equation, when we'll have initial velocity as a function of substrate concentration. And the function that will result from graphing that will be a rectangular hyperbola in that asymptotically approaches maximal velocity. So this value here, and it's fun using your ruler on an iPad, will approach Vmax. So this dotted line, maximal velocity. And we recognize a couple of important things here. First off, let's draw our attention to what is occurring when the concentration of substrate is very, very low. So down here at low concentrations of substrate, notice the initial velocity is very, very sensitive to changes in the concentration of substrate. So at low concentrations of substrate, initial velocity is very sensitive to changes in the concentration of substrate. And so we could even just give ourselves an example of that. We could say, what if substrate concentration changes from my dotted line there to my dotted line here? And yes, indeed, notice that that leads to, we see that that causes large changes in initial velocity. However, as we go out to very high substrate concentrations, so now if we turn our attention, if you will, to a substrate concentration where I'm dotting the green line, and we change that by about the same amount that we did here before. So then what we see is that, if I can hold my ruler properly, is that the change that causes in initial velocity is minimal. Right? In fact, it's hard. I don't have good enough tools to really show this accurately. My ruler is failing me. You know, it's a very small difference right here in initial velocity. So whereas the difference is very large at low substrate concentrations, it's very tiny at high substrate concentration. And recall that we had an expression for this, remembering that when we were looking at saturation conditions, so out where we're approaching Vmax at saturation, where substrate concentrations are very, very high, substrate concentration is, the enzyme is saturated with substrate, we were able to express initial velocity as K2 times enzyme total, because we made that assumption that all enzyme would be bound to substrate at such high substrate concentrations. And as we look at the function, the graphical function, now we can make another simplification or approximation. And that is to say that as we get to really, really high concentrations and we're asymptotically approaching Vmax, we can look at or make the approximation that initial velocity is approximately equal to Vmax. So we now can substitute in for initial velocity, maximal velocity, Vmax equal to K2 times enzyme total. Before we leave this beautiful function behind, I want to make sure that I point out a very important value to you, and that is the Vmax over 2 value. So right here, where the velocity is half maximal, that has a very important definition. So the substrate concentration at half maximal velocity is Km. So this is really important. Km is equal to the concentration of substrate where initial velocity equals Vmax over 2. Excellent. Now we can move on ahead to actually derive the Michaelis-Menten equation and see what the equation is that describes this function. Maud Menten was a brilliant pathologist who worked at the beginning of the 20th century, and one of the things she did was to work alongside with Leonore Michaelis to derive this equation, the Michaelis-Menten equation. Sometime later, there were two scientists working together, George E. Briggs and J.B.S. Haldane, who came up with a simple derivation for the Michaelis-Menten equation called the steady state derivation, and that is what we're going to use today. So steady state, meaning that we're going to make the assumption that enzyme substrate complex is formed as rapidly as it is decomposed. So recognizing two equations that express the decomposition and one that expresses the formation. So if we go ahead and begin by looking at those two that express the decomposition, so K minus 1 times enzyme substrate plus K2 times enzyme substrate is equal to that one by which it is formed, K1 times enzyme times substrate. Now we'll recognize this term here as being enzyme free, and recall that of course that is equal to enzyme total time minus enzyme substrate. And we can plug in that whole conglomeration there for enzyme free. So that's where we're going to go next. And things stay the same over on this side of the equation. Excellent. We're going to begin grouping some of these rate constants. We can get a compilation of terms that can be then expressed as a constant, K minus 1, K2 divided by, we'll just bring the K1 over here, and then we have enzyme substrate, enzyme total, minus enzyme substrate times concentration of substrate. And from there, we can recognize this conglomeration of rate constants as being the Km. That's the term given to that compilation. And we've actually already seen what that means graphically, or how we recognize it graphically. But this makes things simplified a little bit. Concentration of E total. We now want to be able to group like terms. So let's distribute substrate concentration over the right-hand side of the equation. This enables us to bring the enzyme substrate terms onto the same side of the equation. And to pull out enzyme substrate, and to solve for enzyme substrate. Recognize that we had an equation that related initial velocity to the concentration of enzyme substrate, because we recall that the rate limiting step of the reaction is the formation of product, an enzyme. So remember, then we could express initial velocity as being equal to K2 times the concentration of enzyme substrate. So at this point, we can now plug in this entire conglomeration into this equation, which will allow us absolutely to be relating initial velocity to substrate concentration. So we're going to go ahead and bring up a new tablet view so that we can go ahead and do that. So initial velocity is equal to K2 times E total times the concentration of substrate divided by Km plus the concentration of substrate. And check it out. Look at this term here, K2 times E total. This is an expression for Vmax that we recognize. So we can go ahead and simplify and plug in that initial velocity is equal to Vmax times the concentration of substrate divided by Km plus the concentration of substrate. And there we have it. You betcha. This is the Michaelis-Menten equation. And it is, of course, the equation that does describe the function whose graph we have already seen.